Okay guys, now we're going to jump about a bit, and this is going to appear a little bit out of sequence. That's largely due to the fact that for some of you, again, this is the last class of the week, and for others of you it's the first. So I just have to keep all that clear in my head. So this is kind of on a whole other track of stuff. Now, so what we're going to start looking at is how we represent color in computer systems. And by the time we're done with all that, you will understand why hash FF0000 is red, for example. Okay, so that's what we're working towards. We can afford to take our time getting there. So we'll probably take this class and maybe another one by the time we're done. So I find it very interesting anyway, so it keeps me happy. You might or might not find it as interesting. Now, generally, if you have an image that's in black and white, for example, and you want to represent that digitally, black and white is pretty easy, because if you have a shade of grey, it's simply a question of how bright that is, how much lightness is in that. So in some respects, it's like a light bulb, that's with a dimmer switch, and how high is it turned up. So if I was to present you with 20 shades of grey or 50 shades of grey and put them in order, okay, ask you to put them in order, you could do that. Do you know what I mean? Just like, well, there's dark ones at this end of the scale, white is up at the other end of the scale, and it's easy to see where everything fits in. So with levels of greyness, it's very easy to put them in order. And you could see how you might have a range of greys, from 0 to 100 or 0 to 50, and you have 1, 2, 3, 4, 5, 6, 7, 8, and you could assign them numbers that way. So shades of grey, easy to do. In this case, we've got 1, 2, 3, 4, 5, 6, 7, 8. Is that 8 or 9? 8. So you could see how you could have a range. You might say, if I gave you a shade of grey, which ones of these is the closest? And you might give it a value from 0 to 7 or something. But greyness is easy to get a handle on. But what if I was to say, right, I'm going to line you up now based on the colour of your tops. Okay, so we're going to line you up in order. But we know green isn't blue. We know they're not the same. But does green come before blue? After blue? Is green more something than blue? Is it less something else than blue? How do you rank colours? How do you put order on colours? How do you put numbers on colour? That's not as easy to do. Do you know what I mean? If I was to get a Dulux colour chart and cut up the little colour tiles and say, right, I want you to put these in order now. Well, where it was easy to do the black and white, the grey ones. What comes first, I can tell you red is different to blue, and it's different to green, and it's different to orange, but which comes first? And that's a hard question to answer. And that's why it's a bit more complicated to put number on colours than it is to put numbers on grayscale. So that's the kind of questions we're going to be asking now in this class and the next one, I would think. So, green and blue are different, but is it more something than blue? I mean, more what? Obviously it's more green than blue, but I mean, that doesn't help us. So, how can colours be sorted? How can they be ordered? That's a problem. Well, one system we have is the Hue Saturation and Brightness model, or HSB. And that's a system for putting numbers on colour. Now, it's very, very hard, I think, to get your head around the fact that the visible color, the visible light that we see, that we can detect with our eyes, is just a small portion of the electromagnetic spectrum, but that it's one spectrum. So the stuff that's coming out of the RTE transmitter is the same stuff that's coming off my shirt and going to your eyes. It's just with your eyes you can't see radio waves. But it's not that, like, radio is one thing and light is another thing and X-rays are another thing and microwaves are another thing and radar is another thing. It's all the same stuff. It's all part of the electromagnetic spectrum. And we've evolved to be able to see certain ranges of that with our eyes. And different species can see different parts as well. That's a bit of a head wrecker. Like, you learn that in physics class and you can repeat it, and someone asks you, you can say it. It's hard to actually grasp, though, I think. It's hard to actually grasp that it's a continuum and that beyond what we can't see there's infrared, but then beyond that there's radar and microwave. No, way beyond it, like. But it's all part of the same stuff. We can see a small portion of that. So we call that the visible spectrum. That's the visible part of the electromagnetic spectrum, the part that humans can see. Species that evolved on different planets might have, be able to detect different things. No. So the visible spectrum is only a small portion of that. And generally we can see roughly between 700 nanometers and 400 nanometers in wavelength. Okay? So we can see that portion. Now, you could, for example, take colors and order them by their frequency or by their wavelength. So like at the red end there, you've got 700 nanometers. In the middle you'd have things 600, 500, 400. So you could have some sort of a measuring device that measures the frequency of the light or the wavelength of the light, and you could put them in order that way. So that gives us a way to put some numbers on colors. So if I was to give you, each one of those, if I was to give you like a color from each of those zones there, you could line them up in a sort of a rainbow scale. Red, orange, yellow, green, blue, indigo, violet. You could probably put them in an order there using what I like to call the rainbow scale. Okay? And that gives you something. So if I gave you all those colors, you could probably do that. Now, that value there, that's called the hue. And so the hue is where the color would fit along that range of colors there. So the hue is basically a term for its frequency or for its wavelength. Frequency and wavelength are connected by a function. One is the inverse of the other. But that's the hue. So the hue of a color is where it might fit on this rainbow range of colors. But that only gets us so far, doesn't it? I mean, there's no black in the rainbow. There's no pink in the rainbow. There's no brown. There's no grey. There's no white. So there's more to colour than just hue, isn't there? There's more going on than just the hue. So all of these colours here, they have the same hue. They're all bluish. They're all in the blue range. So on the rainbow scale, in terms of wavelength, they're in the blue area. But there's more going on. All of these here have the same hue. But they are different, aren't they? The hue would be somewhere in the yellow. But there's more going on. Similarly, these are down the violet end of the rainbow. So it turns out that color can be diluted. So imagine if you have a cup of coffee, or a cup of tea that's nice dark brown, and you add some milk to it, gets a little lighter. Add some more milk to it, gets a little lighter. Well, color can be diluted, so you can affect the saturation of the color, it's called. So saturation is the purity of the color. So a highly saturated color is very pure, and a color with low saturation is grayish, it's kind of washed out. If you leave a magazine in the back window of the car over the summer and the color fades, what's happening there is the saturation is being reduced. You take a nice bright red shirt and you wash it, 20 times, 50 times, it gets that bit lighter. That's the saturation is being reduced. So saturation is the purity of the color. And high saturation is strong, vibrant color. Low saturation is, washed out. So saturation gives us another way to organize the colors. So whatever about it being green or red or wherever it is on that rainbow scale, we can also talk about the saturation of it. So the colored chips on the left there are very high saturation. But as we move towards the right, the saturation gets lower and lower. So looking around now at your tops, most people have fairly heavily saturated color. Like a bright red Manchester United shirt is going to be, high saturation. Generally, a football team isn't going to go for fairly low saturation colors anyway. So strong color, as we might call it when we're describing it, that's high saturation. So this color here has the same hue, they all have the same hue, and they all have the same saturation as well. But hue and saturation still isn't the full picture. There's one more thing going on. And what did I say they were? There's hue, saturation, and brightness. So here, all these colors have the same hue and the same saturation, and all that's different is the brightness. Now, at least in brightness, we're on familiar territory. That's just how much light is coming off something. That's how high is the dimmer switch turned up, So you could have a yellow light bulb, particular hue, particular saturation, and then you're turning the dimmer switch up and down to see how bright it is. So it gives you hue, saturation, and brightness. And with the three of those, you can pretty much specify any color. Typically, when you're specifying color, you need three different values. Unlike a grayscale where you could just one value how bright it is, hue, saturation, and brightness gives you colors, but even if you're using a different system, you typically need three values. Now, hue is often expressed as a point on a color wheel, or the radius of the color wheel. So hue is typically expressed as a value between 0 and, well, not 360, I guess 359. Okay, because 360 degrees and 0 degrees is the same thing. Saturation is usually expressed as a percentage. So it'd like be 100% saturation or 0% saturation, high and low. And brightness in the hue saturation brightness model is typically expressed as a percentage as well. So if you were to go into PowerPoint or something and you're trying to pick a color for your background, and you have these sliders where you can choose the color, One of the ways you can do that is using the hue, saturation, and brightness. So here the hue is like where you're going around the circle, how far around you're going. So as you can see, it's pretty much our rainbow scale, red, orange, yellow, green, blue, indigo, violet. And the saturation, outside it's heavily saturated. As you move in, it's less saturated. And then the brightness is on a separate scale there. Obviously for 3 variables, it's going to be hard to represent in 2 dimensions. So typically you have things 2 Yokis. Ideally, if you had a 3D display, 3D computer system, you could use your 3 dimensions then fairly easily. So you could go into PowerPoint now or Word or anything and mess around with the hue, saturation, and brightness and get a feel for how that works. In this example here, they're just 3 separate sliders, so you can specify the hue there on the top one. Again, you notice red, orange, yellow, green, blue, indigo, violet. Very much the whole rainbow scale. And that's because that's just the frequency or the wavelength of the light. The saturation then you can slide up and down, and the brightness also. Eventually pick your color. So this shade of purple here, the hue is 329, the saturation is 64, and the brightness is 68. So if you were getting class hoodies, for example, and you wanted to explain to the hoodies are us, you want this particular shade of purple for your hoodies, you might say you want the hue to be this, the saturation to this, and the brightness to be whatever. Actually you wouldn't use the hue, saturation, and brightness system for hoodies, as it happens. There's a better way. You could. Any questions on that? So the hue is easy. That's where it fits on the rainbow. So is it reddish, orangish, yellowish, greenish, bluish, indigo-ish, violet-ish? It's somewhere along there on that scale. Now sometimes it's hard to figure out, but pink, for example, would have a red hue, and then you get the pinkness by tweaking the saturation and the brightness. A grey could be pretty much any color, any hue. It's because the saturation is turned down. It would just be grey. Saturation then is how pure the color is. So is it grayish or is it pure color? And then the brightness then is how bright that is. Light or dark. So if some of you had hoodies with or shirts with the same hue and the same saturation, we could probably line you up in order of brightness. If some of you had clothes where the hue was the same and the saturation was the same, then we could probably line you up in terms of hue and brightness. We could probably line you up in terms of saturation. But when the 3 of them together, it's harder to put order on things. Any questions on that now? So now every time you see a color, you'll be thinking, okay, in terms of hue, where's that fitting in terms of saturation, in terms of brightness, what? Do you know? The door there, right? In terms of hue, where is that?
Orange.
It's kind of orange, somewhere in the orange range anyway. In terms of saturation, is it like oomph? Is it like way orange, man? No. So the saturation is turned down a bit. No, not a huge amount, but it's certainly off 100%. And in terms of brightness, it's reasonably bright. We could experiment, see if we could reproduce the color of the door and see what the hue, saturation, and brightness would be. Now, obviously, of course, the hue, saturation of that door there, as it's coming to my eyes, is very different now with the lights off than it will be when I turn the lights on. It's going to be much brighter with the lights on. In fact, the hue, the lights might even cause the hue to be different. These lights tend to be fairly green or blue, but our brains compensate. That's into a whole other thing then about calibration. Now, so hue, saturation, and brightness is probably the most natural way to think about color. First of all, because, we all know what rainbows look like, we've seen them. We can understand the concepts of saturation, if it's strong or not, and how bright it is. Most computer systems though use something else. One of the advantages actually, if you do use the hue, saturation, and brightness for images, to get a black and white version of your image is trivial, because you just ignore the hue and ignore the saturation and just take the brightness values. So if you had pixel by pixel, if you had the hue, saturation, and brightness of each pixel in your image, to get a black and white version, you would just take all the brightness values for your black and white image. So it does have some advantages. For analog television, people liked to work in something like HSB rather than some of the other systems. But the main one people use now is RGB. It's the main one we use for computer systems. Okay? Anyone heard of RGB before? Red, green, and blue. Does anybody remember this diagram from physics class? Nobody did physics? Yeah. So, if you have a red torch and a green torch and a blue torch, and they were all shining on the same spot, it could actually look white. When you mix red, green, and blue together, you get white. If you mix red and green together, you get yellow, which isn't as intuitive as you would think. If you mix red and blue together, you get purple. I can believe that. And if you mix green and blue together, you get that lighter blue there, cyan. So this is the RGB system. So in the RGB system, a color is represented with three values: a red value, a green value, and a blue value. And the red tells you how much red is in it, the green tells you how much green is in it, and the blue tells you how much blue is in it. Now for some colors that's easy, others not so much. So if you take this man's red hoodie there, the red value for that hoodie is probably fairly high because it's like way red. Okay, man down the back there with the blue top, you'd be fairly convinced that the blue value, for that would be fairly high because it's way blue. Other things are a bit more complicated, less intuitive. So let's have a look at some of those. So this red here, now for the RGB system, we usually go from 0 to 255 rather than from 1 to 100. Why do you think we go from 0 to 255? Any takers? Why 255 though and not 355? Kinda. What's special about 256? Means nothing to you, no? In 3 weeks of computer science. Week 4 now. Yeah, the bits and the bytes. With 8 bits, you can have 256 possible different values. So if you go from 0 to 255, that's 256 possible values, which is what you can do with 8 bits. And since most memory is organized along 8 packs of bits to bytes, we organize things that way. So in the RGB system, we can go from 0 to 255, which requires 8 bits, 0 to 255 for the green, and 0 to 255 for the blue. So that would take 3 bytes altogether, or 24 bits. Have you heard of a 24-bit color, 24-bit graphics card? 32-bit graphics card. So that's what they're talking about. The more bits you have per pixel, the more possible different shades you can display. So we're going to use 24 bits for each color. So to specify a color, you need 24 bits in this scheme. Which gives you how many? Anyone want to speculate? Well, it'll be 256 by 256 by 256, which I think is about 16 million or something. So you may also see specified if you're buying a PC or something, graphics 16 million colors. 24-bit color. So, this here has the red turned way up to maximum, and the green and the blue are set to 0. So that's why that's like way, way red. And this one here, the blue value is set to 200. There's no red and no green. So it's not quite full-on blue, but it's up there. Now, when you mix red and green together, you get yellow. So if the red turned up full and the green turned up full, you're going to get full-on yellow. And I think we can all agree yellow doesn't come more full-on than that. Okay, so that's the red value is 255, the green value is 255, and the blue value is 0. Here, there's no red in this. The green is quite high, about half. Well, it's about halfway, isn't it? Slightly more than halfway. And there's no blue. So if you didn't have this color in front of you, you couldn't see the color if you just had the numbers. You could tell, well, green anyway is the only color that's in play. So it's just a question of how green it is. And it's quite green. Fairly high value. Here, again, only green is in play. But because it's a lower value, it's darker. Now, no red, no green, no blue at all is black. So as this green value, if we were to continue to drop this green value and get it lower and lower and lower, we'll be heading in the direction of black. If we crank the green value up, we'll be heading in the direction of full-on green. So as this value gets lower, the green will become darker. So that's how this system works. Low values are dark, high values brighter. Now, if the red value and the green value and blue value are all the same, you get a shade of grey. In the RGB color system, so how many different shades of grey can you have? 256. How kinky would that be? So, the red, the green, and the blue are all together, are all the same. It's a shade of grey. 200, 200, 200 is quite bright, isn't it? Because 200 is fairly high. That's why it's quite a bright grey. If that was a lower value, they were all lower, it would still be grey, but it would be darker. If we reduce that down, it's getting darker again. No. 255, 255, 255 is maximum red, maximum green, maximum blue. That's going to be white. It's hard to imagine, I think, how putting red and green and blue together would give you white. Certainly doesn't work like that with your set of paints in school. You'd be there forever mixing paints to try and make white. Would never happen. But with light, it's different. So red, green, and blue, all turned on full. That gives you white. What side is coming next, do you think? So 0, 0, 0, black. No. So in HTML then, we use the RGB system to specify the colors. But we use hexadecimal. Have you seen hexadecimal yet? It's a numbering system where you, when you get to 10, instead of doing 1, 0, you go like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So it's how we would be counting if we had evolved with 16 fingers instead of 10. We do that because it fits in nicely with the way bits and things work. So you'll see the hexadecimal system in computer architecture or something. So here on the left, we have a red value of 128, a green value of 128, and a blue value of 255. Now, in hexadecimal, 128 is 80. So the red value here is 80, the green value is 80, and the hexadecimal for 255 is FF. So if we say hash 8080FF, that gives us that shade of blue. On the right there, the RGB value is red 0, green 255, and blue 128. So the hexadecimal for 0 is 0. The hexadecimal for 255 we saw was FF. And the hexadecimal for 128 is 80. So this color is hash 00FF80. So that's where all those color codes came from. So when you Googled HTML color codes to get different color codes, that's where they came from. So with the RGB value, you should be able to calculate the hexadecimal and specify that. No, actually, as it turns out, in most situations, you can also just specify the RGB value as well. There's a different syntax for that. So a lot of time you can say RGB open bracket 128, 128, 255, close bracket. And in most situations, that will be fine too. Any questions on that? No. Skip past that there. It's just showing you that in an image might be stored with the red part, the green part, and the blue part. Separate channels, we call them. When you put them together, you get the image, but we're not so interested in that. So typographically there, that's screwed up. But in your HTML, in your CSS, for example, you could say body, background, hash F0AC75, semicolon, that would specify the background color. No. It's pretty much the same thing again. Okay. This one is the red value is 187, the green value is 224, and the blue value is 227, which gives you BBE0E3. Now, as with most colors, you do see them better if you have your eyes open. So, hello. No? Okay. No. So, have a look here now. What's your name? Aiden. So, Aiden. 333399. What do you think that might be? So, there's red, green, and there's blue in there. Which of those colors, the red, green, or blue, is dominating? Which one is the highest value? The blue. So we know whatever's going on, blue is winning out there. There's more blue than anything else. Okay? So is the blue value high? I mean, it's about halfway. No. If it was 000099, it'd be only blue at work. Okay? But with those values coming up behind the red and the green, it's pushing it away from black in the direction of white. So my guess would be, well, we know it's blue anyway. My guess would be that it's kind of a darkish blue, I would think. But that's darkish. Yeah. Okay. No, you wake her up there. What's her name? Tracy. You're up next. FF8888. What might that be? So which of the colours there is the strongest? Red. So the red is winning out there. And is it high or low? It's as high as you could get, right? So this is as much red. This colour has as much red in it as you could possibly have. No. What's going on though with the other two values then? The green and the blue. They're the same. And they're fairly high or low? High-ish. No. This is a tricky one, I think. If this was A8, 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 what would be happening? Do you think? It would be grey. Yeah. If it was A8, 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 it would be grey. And it would be fairly bright, a bright grey, wouldn't it? Fairly light. So imagine we had A8, 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 we had a bright grey, and then we cranked up the red part as high as it would go. What might grey with some red on look like? You know, you're cooking a grey dish, flake in some more red. What might we end up with? I think pink is a good bet. Yeah. Okay. No. Next up there. 0CFF00. What might that be? So which color is dominating there? Red, green, and blue. Green. No. Is the blue value high or low? It's 0. So blue isn't in play here at all. What about the red value? Yeah, only a tiny bit. Really, the red value isn't worth talking about. I mean, 0C in the grand scheme of things, might as well be 0. So really, this is mostly red, green, blue, RGB. It's mostly pure on, full on green, I would think. So we should see a very strong pure green. Yeah, they don't come brighter than that really. Next up there, we have BBF2AB. What's the stronger of the three colors there? Green. Now, in this case though, the red and the blue are quite high, aren't they? They're certainly in play. They're also quite close, aren't they? So what, he says. So imagine it was like, say, BB, 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 right? Which would be a bright grey, and then we turn up the green. You know? So I think what we get is we'll get a pale green. I think this colour will be to green what the other colour was, what pink was to red. So I would say a pale green would be my guess. All right, that's quite pale actually. Okay, now, easy one for you there. FF. Yep.
White.
Yep, pure white. Okay. Quite easy one for you there, sir. 80. Grey, yeah, because they're all the same, it's going to be grey. It's going to be light or darker in the middle. It's going to be in the middle actually. I think 80 is pretty much as middle as you can get between 00 and FF. So it's pretty much 50% grey-ish. Next up you there, sir. This is a tricky one, I think. So the red here is quite high, FF. the green is certainly in play. It's about halfway cranked up. And the blue isn't really in the game at all. So we'll ignore the blue. Okay? Do you want to hazard a guess now, or will we talk about it some more? What would happen if you had the if the red and the green were full on? What would it be? Yellow. Okay. Now in this case it's not a yellow because there isn't enough green in there. There's only half enough yellow really to make it green. So to make it yellow. It's only half enough green to make it yellow. So if you were heading in the direction of Yellowville, but went too far towards Red Town, where would you be? Yeah, Orange Land, I think. Yeah. Okay. Next one up there. D is high-ish, yeah. D1 would be high-ish. Fairly, be quite high. Be higher than all the others anyway. So here, the red, green, blue. Blue is the one that's winning out there. The others are quite high though. So it's going to be blue. It's going to be light blue, I would think. And the red sort of edged up a bit. So the question is, has it pushed it far enough to kind of be purpley? My guess is no, actually. I don't think the red is that significant. Oh no, that's purple, all right. Yeah. Okay. So well done there with purple. Easy one for you, sir. FFC's2? Yeah. Strong yellow, dark yellow, bright yellow. Pure yellow? No. We know it's not going to be pure yellow. That C there is high, isn't it? So be very whitish yellow. Okay, you can hardly see the yellow there. It's so light. Next up there, sir. 1589-83. Well, so the red, the green, and the blue. The green and the blue are at work there, aren't they? Yeah. Which would, if green and blue were full on, what would you get? Cyan. Okay. Now they're not full on, so it's going to be a dark cyan, whatever that might be when it's at home. And the red isn't really at work there, so it's going to be some form of blue. Oh, okay. Not what I was expecting, actually. Next up there, BE844A. What's winning out here is the red, isn't it? If the red and the green were full on, what would you have? Red and green together give you yellow. Okay? But here, the red is pushing ahead really in terms of red versus green. So I think you're talking a reddish yellow, which we might know as orange. Would it be pale? Would it be pale or dark? Would it be that pale and orange? I don't know. I'm thinking it'd be kind of dark. All right, we're all wrong. Okay. Yeah. Okay. No. Next up there. 950303. So the red here is winning out, isn't it? Are the green and the blue worth talking about? No. So this is mostly red. Would it be? And it's not full on. It's about halfway. So it would be a strong but dark red, I would say. Oh yeah, totally on. Right. Okay. Now, next up, sir. 5FFB71. The red and the green and the blue. The green is the winner here. The others are close behind though, aren't they? Do you know, well, first of all, the other two are equally balanced. So it's not going to push because the red and the blue are quite similar, it's going to push the green in the direction of white. It's not going to steer it towards, orange or whatever. So my guess would be, well, what would your guess be? I mean, it would be a palish, brightish green, I would say. All right, I suppose, yeah. Oh, yeah. And you, sir, easy one for you? Black. Okay. No. So, mystery solved then. Okay? So those freaky numbers, that's all they're saying. How much red, how much green, how much blue? Yes, sir?
Will you explain the letters again? A, B, and C.
No. 1 minute to go. So I'll do that in the lab. You'll see them anyway again, okay? I have to be somewhere else in the next class, sorry.